Good afternoon, everyone. Welcome to the Wednesday session of the European Quantum Week. My name is Thierry Bucher. I'm the coordinator of the project Asterix, and I'm the chair of the Science and Engineering Board. And I will be the moderator of this session today. Yesterday, we had an introduction to the quantum flagship projects by the European Commission. Then we had the presentation of the projects about sensing, and then the projects dealing with simulation, and then projects about basic science. Today, we will have the presentations of the projects which are working on quantum computing. Then we will have the projects working on quantum communication. The presentations will be divided into blocks. The first one about quantum computing. Then there are 4 presentations given by projects AQTION, OpenSuperQ, Square, and microQC. And then there will be time to questions and answers. And then there will be the second block about communication and basic science, where we will have the presentations of the project CiViQ, TIA, QRANGE, UNIQORN, and to the SIPC. And then we will have some time for questions from the audience. So now I would like to start with the presentation. And the first presentation is the project AQTION, which is coordinated by Thomas Mons, and who will give the results of this project investigating quantum computing with trapped ions. So Thomas, the floor is yours.
Greetings everyone and welcome to the European Quantum Week. I happily give you a status report and a brief explanation about the goals of the AQTION project. In the AQTION project, we are an initial collaboration of outstanding experts working on Eintrap-based quantum computing, and we pursue the joint goal of putting an experiment that usually would be found in an optics experiment covering 10, 20, even 40 square meters of lab space, but we want to put that now into a normal industry rack system. That means that our system is directly compatible with, for instance, the installation in a high-performance quantum computing center, in a normal classical computing center. It can be installed with a bank, or it can be installed in, for instance, specific system for chemistry research. In order to achieve that, we've been really trying to push and get everything from lasers to vacuum chamber to electronics into a rack standard and control all of that from a mere simple laptop if need be. In order to do that, we have been pushing towards the miniaturization and stabilization of our systems, and happily I can now say that this has been achieved. So this is for the first time a quantum computer that operates at room temperature, is readily available via the cloud, and is installed in a normal environment. We've been able to do that now in such a way that we control up to 50 qubits in our system. We've been able to do that now with respect to access from a normal laptop using various software development kits, and we support the majority of those that currently exist worldwide, including the access possibilities offered by our partner in France, which is Atos, one of the leaders in quantum algorithm research. In addition, it's really important that this system not just exists and you can use it, but you have to make sure that it operates at the ultra high level of performance so that interesting algorithms can be implemented. We've now changed and automated the system a lot in such a way that at the push of a single button, the PhD students in our lab can achieve entangling gate operations which build the foundation of quantum algorithms with error rates as low as a few in 1,000. And we can do that not just with our quantum registers per se, but our colleagues in Oxford have been able to realize that with 2 different species. And because you can entangle 2 different species, that's the ideal foundation to show then later on you can achieve entanglement, for instance, across 2 vacuum chambers, across 2 quantum processors to build networks of quantum computers. When you have such a great system, what would you do? Well, you want to push and get more and more algorithms out. However, as I mentioned, there are a few errors sometimes popping up, and you have to correct for those. One particular error is called qubit loss, and recently we've been able to publish the experimental realization of the correction of qubit loss in our system with our colleagues in Jülich in Nature, and that's been the first experiment ever along those lines on international level. In addition, we've been working now on scaling up the system. So imagine you have these algorithms, everything works, but you want to work with more and more qubits. In order to work with more and more qubits, you'd have to say, how do I get from 10 to 50 to 100 to 1,000 qubits? So our friends at ETH Zurich, for instance, they have been pushing towards integration of optics directly into microfabricated ion traps. And we see the first results coming from those devices with low error rates, notably less than just 1 in 100. And furthermore, these efforts are supported by our friends in Jena, by Fraunhofer, who are installing optics directly into our systems. If you have that, we now managed to show that we have a system in a rack. We have been able to show that we can operate these systems at high fidelities. We can implement algorithms. We have set the path to get towards from 50 to 100 qubits and do that with high performance. The next question is, similar to what we do with our classical computers, you'd have two computers, you want to connect them. And friends in Oxford, for instance, have been able to show that they can entangle two different separate quantum processors via exchanging light at high fidelities more than 100 times per second. And these efforts go hand in hand with efforts from our colleagues in the Quantum Internet Alliance, for instance by Ben Lanyon and Tracy Northup, who are currently working also in Innsbruck on a fiber connection across the campus to connect two quantum processors. And with that overview, I hope that I've been able to convince you that we have now achieved almost all the goals that we've set for our project. So we have realized the quantum computer. It fits into 19-inch rack standards. It works at fault-tolerant performance level. It is scalable, and what remains to be done now for the remaining year is to demonstrate a quantum advantage based on the results from the European quantum flagship in order to demonstrate that Europe can lead the second quantum revolution. And so I'd like to point out that all the great results that I have now shown you are obviously not just done by our local PhD and postdocs in Innsbruck, but this is an outstanding and probably a world-leading consortium that we have realized in action. And it consists of partners, for instance, in Oxford, both theory and experiment. We have friends now in Jülich. We have colleagues in Madrid that support these efforts on the theory side. We have ETH Zurich and the team of Jonathan Holm, where we are pushing towards scalable ion traps, in addition to the efforts, for instance, by Mainz to work on shuttling ions for scalable quantum computing. Besides these research and academy-based partners, we also have a couple of industry partners that greatly support the goals of AQTION. And in particular, there is Atos, one of the leaders with respect to quantum algorithm development. They have direct access to the devices in Innsbruck. Fraunhofer was a great help in order to push for optics. ACRA is supporting Mainz with respect to electronics. And finally, Toptica is probably one of the leading experts in terms of laser control, which is used in all the systems in our consortium. And in that respect, I'd like to thank both my collaborators, but as well as the audience on behalf of the AQTION team for all the support and research.
Thank you very much, Thomas, for presenting these impressive results on trapped ions. And then now we will go to the other project, which will be presented by Frank Willem Maur, the coordinator of OpenSuperQ, and who will present us results about superconducting qubits. So Frank, the floor is yours.
So my understanding is that somebody starts a recorded presentation now. presentation of the project, an open superconducting quantum computer, or OpenSuperQ for short. I'm the coordinator, Frank Wilhelm Mauch. Some basics about our project. It is running, as all the other flagship projects, for a bit over 2 years now, for 36 months. We have 10 partners from 5 countries who strive to jointly build a hybrid high-performance quantum computer that can outperform classical computers and make it available at a central site for external use. If you look at our project partners, you see we have a combination of universities, research and technology organization, and industry partners. All of the industry partners are small and medium enterprises. And if you look at how we are sharing our roles, you see that the core quantum research and development is still mostly happening at universities. Things like application development, as well as chip fabrication and measurement infrastructure. On the other hand, a quantum computer is much more than just the core quantum part. It needs to be a functional machine within a scalable engineering infrastructure. And here, the heavy lifting is done by our industry partners who are specialists in enabling infrastructure that is needed for quantum computing, and they're doing some bespoke developments for us. And in between those are the research and technology organizations who are covering the important surroundings of the quantum part, which on the one hand is too specialized to be already marketable for companies, and on the other hand takes the long-term perspective and professionalism that those organizations have that is often difficult in universities. We also have an advisory board of distinguished scientists. We have a science board with colleagues in our field with who we are exchanging experience in some components. And we have a user board of companies who are interested as users to get a first look at what we develop. So let me show you a few examples of the different stages of our project. Our quantum computer is sitting in classical infrastructure that provides the necessary cooling, as seen with the cryostat here. It has to be run by tailor-made electronics that is flexible enough for development, but scalable enough to run such a large machine, and that also is run by the necessary software. Around our quantum chip, where there is a package to connect it, which you see at the top left, and the chip itself has a layout that you see on the bottom right, with qubits shown in blue, connectors shown in green, and red curly lines that you see on top that are coming out of the plane, which indicates that this is a three-dimensional object. It's not just living in one layer. And this is, in fact, one of the challenges. The curly lines are resonators, and they are curly because they support standing waves, so they need to have a very specific length. Inside the chip is the actual qubits. They're based on Josephson junctions, and in the left panel, you can see a cross-shaped qubit where the 3 lower legs are for the connectivity. The lower leg is for input and output. The right and the left leg are for connecting to other qubits. And on top, you see the actual active part that makes it a qubit, which is zoomed in on the other panel. You see there a cross between wires. This is where the Josephson junction is sitting, the nonlinear inductor, and this whole object is called a superconducting transmon qubit. Our software will run in a central facility with a programming interface and be connected to a high-performance computing environment because the first generation algorithms that we can test on it are all hybrids with classical algorithms. This was basics. Now let's look at achievements. We have, in fact, developed the whole cryogenic and readout and output environment for running a 100-qubit system. You see this very delicate setting. The brass plates are to keep temperature constant. This whole object is sitting in a cryostat, and you see the careful wiring that goes to the chip, which is actually hanging at the bottom of the top. Once we are reading out information, it's important to amplify the very weak quantum signal. And for this, we have developed all European quantum amplifiers. So they are amplifying as carefully as quantum physics actually allows us. and they are called traveling wave parametric amplifiers. And the elements that you see on the left are, again, our friends, the Josephson junctions, which are now put here into a series array to reach amplification. In the middle, you see another of these amplifiers in its whole chip, where the bent lines show you where the Josephson junctions are. And on the right, you see how this very well discriminates 0 and 1 as the blue and red areas. This was an important development for us because the international supply of these amplifiers coming from the US got a lot more complicated in 2019 due to export restrictions. Now, to actually accomplish reading and writing to our quantum computer, we need control electronics shown on the right that has an experiment called a PQC, which is orchestrating the electronics, and then generators that send microwave pulses to the qubit to manipulate it. But this also needs the software to calibrate this. Quantum information is very fragile. A system needs very careful calibration. So you see on the left that we have a software package that finds the optimal pulses with which you can implement gates, but also continuously characterizes the system better and better to ensure reliability and fast ramp up. This is called the C3 software package. What we would like to run on this are typically variational algorithms where we use a quantum computer run in a simulator mode of operations that calculates a quantity. Here's a quantity called G. That is very hard to compute on a classical computer, but easy to read out. Then we use a classical computer to evaluate, have we already reached an optimum, that then suggests new parameters to the quantum computer to evaluate our quantity another time. By this hybridization, we can deal with limited hardware because while the quantum classical computer is working, we can reset the quantum computer and by this eliminate errors. An important application for these early algorithms is in the simulation of molecules, as shown on the left. And we have developed a whole suite of different clusters that are also scalable, like water clusters or also hydrogen cyanide polymers, which are very important in prebiotic chemistry. And those we can test on the upcoming larger quantum computer platforms. We have also looked at how to best program the quantum computer. And on the right, you see a circuit diagram. And you do not need to focus on the detail. You just see that there's different types of blocks. The purple ones are those that conventionally occur in quantum computers, but we try to make diligent use of blocks that typically are not in the software library, but that are easy to make, like the green blocks, and that we can then use to speed up compiled algorithms. And here is a concrete example of this. This is our implementation of the quantum approximate optimization algorithm, which is used for solving the optimization problems that are often at the core of modern computing, including machine learning and artificial intelligence. We have tested this for an aerospace application called the tail assignment problem, which is a very hard computational problem, and shown this is a suitable approach. Again, here you see that the quantum computer is reprogrammed by a classical computer to achieve faster optimization that is quantum enhanced. Now, when you program this, the step from the classical computer to the quantum computer requires a compiler that breaks down the commands that you would like to run to the commands that the quantum computer can run. However, our colleagues at ETH have in our 7-qubit flagship device shown, you see on the left, you see a picture of the flagship device, and they have shown that they can avoid compilation by actually natively implementing a very large set of commands, including those parameterized by a continuous set of numbers. This is shown in the middle. You see calibration curves, and they can essentially move the green dot wherever you want. And by this, they were able to run the algorithm a lot more efficiently than usual, and they have actually broken the world record in depth. So in the number of steps in the quantum algorithm, simply by clever compilation. And this is, in fact, one of the raison d'etre for our project, which is that the deep access and the creative use of hardware that we can have as a European nonprofit allows us to come up with creative solutions that lead to disruption in applications, there is no walled garden by a company, and there is also no export restriction. You see that we have developed our key technologies and components, and the system integration, which is the goal for the rest of the project, is on its way. Thank you very much for your attention.
Thank you very much, Frank, for this presentation of the impressive progress in the superconducting qubits for quantum computation. Now we will move to the following project, which is the project Square, and which is coordinated by David Unger from Karlsruhe Institute of Technology. In this project, they are using rare earth ion doped crystal to develop scalable quantum computing and also to perform quantum sensing. And now, David, the floor is yours for the presentation.
Hello, my name is David Unger. I'm the coordinator of the Basic Science Project Square, and I have the honor to present our results. Our ambition is to push the challenge to find new qubit implementations which have good scalability prospects. And our approach is to use rare earth ions in crystalline materials and to use them as qubits. The idea is to use the spin degree of freedom to encode logical states and to read them out optically. In general, multiple ions can be addressed to form a multi-qubit register and thereby form a quantum node, which can be also interfaced to distant nodes via photons. And our ambition is to show the potential of rare earth ions to realize such scalable quantum computing nodes. Why do we believe that rare earth ions are particularly suited for that? First, rare earth ions have already demonstrated outstanding quantum coherence. Such superposition states of spin states have persisted for up to hours. And then second, it was also already shown that one can address multiple ions even within a single nanoscale volume in frequency space. Each ion has a slightly different transition frequency, such that one can selectively address them with a narrowband laser. Furthermore, rare earth ions can also be used to realize fast quantum gates, because if ions come very close, they interact very strongly. One ion getting in the excited state will shift the transition frequency of a neighboring ion, and this can be made of the basis for a quantum gate. And finally, rare earth ion materials can be engineered to a large extent, such that one can integrate them into photonic devices in a scalable manner. Based on these beneficial properties, the specific goals of the Square project are to demonstrate the basic elements of such a quantum computing node. And the first point is to demonstrate efficient single ion addressing. However, the ions interact only weakly with light fields, and one needs to enhance this interaction. Our approach is to use optical microcavities, like these fiber-based microcavities or such integrated devices, to enhance the emission and get efficient access to single ions. With this, we want to demonstrate high-fidelity single and two-qubit gates. We want to realize such an optical interface that allows one to interconnect distant quantum nodes. And we want to look at a scalable implementation by looking at protocols that describe such systems, develop materials and devices to make up a technology for this approach. Let me now share a few results that we could achieve during the first period of this project. And the first big success was to demonstrate single qubit control. We were able to isolate individual cerium ions in a crystal and to manipulate its spin degree of freedom with microwave pulses. And here you see the coherent manipulation of this electron spin. And by watching the behavior of the electron spin, we were able to identify the coupling to a nearby silicon nuclear spin. Such nuclear spins can have very long quantum coherence lifetimes and can thus serve as a quantum memory. A second set of experiments relates to the enhancement of ion emission with the help of a cavity. And in one experiment, we were able to enhance the emission of erbium ions, which emit a telecom wavelength, by coupling them to a tunable fiber cavity. Here you see the emission of the ions without the cavity and the enhancement that we get if we couple them resonantly to one cavity mode. Furthermore, by dynamically tuning the resonance condition, we were able to quickly switch between these two situations. And here you see how we could turn on and off the coupling of the ions to the cavity and thereby shape the emission and control the photon wave packet. In similar experiments, by using such integrated disk cavities, which are doped with ytterbium ions, we could also demonstrate a cavity enhancement by up to a factor of 5. Another central point is to look at scalable implementations, and one key device is, of course, the rare earth ion doped materials themselves. And therefore, we looked into the growth of doped thin films. And here you see a first successful device of thin film on a wafer scale, where optical spectroscopy already showed very promising optical coherence properties. An alternative approach is to use nanocrystals. Here the ions are very closely confined, which is beneficial for the strong interaction required for quantum gates. And here we could demonstrate nanomaterials with record coherence properties, in particular for praseodymium and erbium. And finally, we looked into an approach to implant high-quality bulk crystals with ions. And here you see a successful implantation of individual praseodymium ions. The second key device is optical cavities. And such microcavities are actually important tools for a variety of quantum technologies, which motivated us to commercialize fiber-based cavities. And we have founded a spin-off company, Qubit, which started to distribute such devices. The alternative approach is to fabricate microcavities on a photonic chip. And here we are working with doped lithium niobate, which has the benefit of being electro-optically tunable, and where a large number of cavities can be produced on a chip. We also developed various devices which integrate these elements. And one device shown here is a stable cryogenic cavity nanopositioning system with which such fiber-based cavities can be operated within a cryostat. We also developed a scheme for a highly tunable laser source that can address up to 100 qubits in frequency space, where we need to switch back and forth between different frequency channels in a rapid manner while maintaining coherence. And finally, we also devised a blueprint for an all-European cryocooler, which can achieve down to 1 Kelvin temperatures. Another key requirement is to see how well such a multi-qubit register can actually perform. And therefore, we have executed detailed simulations of one example material system, namely europium-doped yttrium orthosilicate. And we found that despite the complicated level scheme, one can achieve single qubit gate infidelities or errors, which are on the 10 to the -4 level. And then by randomly placing ions into such a simulated crystal, we can look at how the ions interact and how well 2 qubit gates can actually be performed. And we found infidelities as low as 10 to the -3, such that together these two numbers predict that quantum error correction should be possible. And then we looked further at how many qubits will be actually connected and available for a multi-qubit register. And we found that there is a qubit chain forming which can extend to up to 100 qubits if the doping concentration of the crystal is high enough, which allows one to really have a large multi-qubit register within a single quantum node. We went further to study scalability also on a higher level, namely on what happens if you connect different cavities and produce an entangled network of multiple nodes. And there we found that one actually needs a new theory that describes in more detail the interaction of quantum pulses with cavities that contain single emitters. Here you see an example how the wave packet of the photon is distorted in a non-trivial manner, and we have developed a new input-output theory for quantum pulses that can capture these properties. We then started to work on a roadmap to condense all this content into one document, where the core is an analysis of the quantum computing and networking capabilities of rare earth ions, including the technological aspects of the implementation, as well as a comparison to established platforms. With this, we hope that we can contribute to the grand vision of realizing a network of distributed quantum computers. With this, I conclude and thank you for your attention.
Thank you very much, David, for this presentation of this very successful results and very promising results about rare earth doped ions in crystals. Then the next presentation will be given by Nikolai Vitanov, who is the coordinator of microQC. MicroQC deals with a microwave in order to drive ion traps for quantum computing. Nikolai Vitanov is at the University of Sofia in Bulgaria. He is a member of the Bulgarian Academy of Science. He is a theoretician and he is addressing many fields, including trapped ions, trapped atoms, doped solids, and classical optics. So now the floor is to you, Nikolai, to present the results achieved in microQC.
This is the microQC project. This is a basic science project, and the acronym means Microwave-Driven Ion Trap Quantum Computing. It has three components. First of all, it's about quantum computing. Second, it uses trapped ions. Third, and most important, it uses microwaves instead of lasers. The consortium is formed by 5 groups. 2 of them are theoretical, my group at Sofia University and Alec Retzker's group at the Hebrew University of Jerusalem. The other 2 groups are experimental, 2 German groups led by Christoph Wunderlich at Siegen and Christian Ospelkaus at Hanover, and 1 UK group led by Uni Hensinger at Sussex. Our microwave-driven approach can be considered as an alternative of the mainstream laser-driven approach, which has achieved spectacular results over the last 25 years, and it is rightfully one of the leading quantum computer platforms. It is quite natural to use lasers to drive trapped ions, for example in the Raman configuration shown here on the top, because laser light carries large momentum. This momentum is very essential to couple the internal transitions of the qubits to the external degrees of freedom, that is, the motion, which is mandatory for the creation of entanglement and conditional gates. However, the problem that this approach faces is that it requires many optical elements placed on the top of an optical table, as seen here on this picture from Dave Whelan's group at NIST in the United States. The ion trap hidden here somewhere on the optical table is dominated by many optical elements. Although this is a feasible approach for a few qubits, or even dozens of qubits, it may be a challenge if we want to scale this up to hundreds and thousands of qubits. It would be very convenient if the qubit transition, shown here in orange, can be driven directly by RF or microwave fields instead of lasers, going via an intermediate state. However, this idea has its problems because microwave and RF fields have very small momentum, and therefore they produce very small coupling between the internal and external degrees of freedom. Therefore, nobody considered using them until 2001, when a breakthrough occurred. In 2001, Christoph Wunderlich, who is the head of the Siegen group, proposed the idea to supplement the microwave drive with a static magnetic field gradient. He was able to show that the so-called effective lambda parameter, which quantifies the coupling between the internal and the external degrees of freedom and measures the gate speed, is proportional to the magnetic field gradient. Therefore, a strong magnetic field gradient can produce a large coupling and fast gates. This approach is now followed by the groups in Siegen and Sussex. A little later, Christian Ospelkaus, who heads the Hanover group, showed that one can achieve similar results with an oscillating rather than static magnetic field gradient. It brings some advantages because it can achieve larger gradients, although it also brings its own challenges. The main objective of microQC is to demonstrate through state-of-the-art quantum engineering fast and fault-tolerant microwave to qubit and multi-qubit gates, and to design scalable technology components that apply these techniques in multi-qubit quantum processors. The successful accomplishment of these very ambitious objectives in a combined efforts by the 5 groups in the project will hopefully make large-scale quantum computation and simulation with microwave-controlled, microfabricated surface ion traps possible. Our work is organized in 3 interconnected work packages. The first one is on technological development. It's very important because it will allow us to produce microfabricated surface ion traps, which are very resilient to noise and which will also allow us the application of large magnetic field gradients, which is crucial. With these traps, we hope to construct high-fidelity and high-speed few qubit gates beyond the quantum error correction threshold. The third work package will use these achievements for scalability to many qubit systems. In the end of the project, we intend to produce a roadmap to high-technology readiness levels. 3 features are very important to our approach. First, we use silicon microchip technologies, which are very similar to conventional computers. Very importantly, we use microwave technology, which is compact, very well developed and present in today's mobile phones and many other devices. The third is that we execute quantum gates by the application of voltages to a microchip, again similar to conventional computers. We hope, based on these 3 features, that this is a platform which can scale up to millions of qubits, at least according to current state of the underlying science. In the next slide, we see some results from work package 1, which is technological development. On the left, we see an electronic quantum computer model produced by the Hanover Group by microfabrication in a clean room facility. In the middle, we see how it looks when assembled. It is a highly complex structure consisting of several layers with oscillating and static gradient current carrying wires, electrodes, silicon nitride grating for individual optical addressing, integrated photon detectors, trench capacitors, etc., etc. It looks very similar to the classical microprocessor chip shown here on the bottom right. On the top right, we see a real picture of another quantum computer model produced by the Sussex Group. The next slide demonstrates one of the advantages of the microwave approach. When we perform a single qubit and 2 qubit gates, we want to make sure that the neighboring ions are not affected by the fields that address the target ions. In the laser approach, this might be a problem. In the microwave approach, the magnetic field gradient makes the transition frequency of each ion different because the ions are located in different points in space and therefore experience a different Zeeman shift of their transition frequencies. In the picture on the top, for example, we see that omega-1 is much smaller than omega-2. Therefore, individual addressing can occur in the frequency space, as shown here in the picture in the bottom, rather than in real space. This is a big advantage for the microwave approach. So far, the crosstalk has been reduced to very low levels with the static gradient approach. The Ziegen group has reduced the crosstalk to levels 10 to minus 5 in a register of 8 ions, and the Sussex group has reduced it to less than 10 to minus 7 with a pair of ions. The Hanover group currently has a crosstalk of 10 to minus 3, but there is a strategy to reduce it significantly by using the narrowband composite pulses developed by the Sophia group. Narrowband pulses allow one to cut off the wings of the excitation profile so that if we address the ion shown here in the middle, then the neighboring ions, although they do see some field, are not affected due to destructive interference of excitation pathways. In this slide, we show some results from work package 2, which concerns high-fidelity 2-qubit gates. In the top left, we see some results from the Hanover group. They obtained 99.7% fidelity of a 2-qubit gate by amplitude pulse shaping. In the preliminary results, they had actually a lower fidelity of about 98%, but by using broadband composite pulses developed by the Sophia group, they managed to increase the fidelity close to the fault-tolerant threshold level. In the bottom left, we see some preliminary experimental results of a 2-qubit phase gate by the Ziegen group generated by dynamical decoupling sequence. It is very important that in this gate, the gate speed scales with the square, and actually faster than the square, of the magnetic field gradient. So, larger gradients can boost the gate speed considerably. In the middle picture, we see the concept of a multi-tone 2-qubit gate developed by the Sussex group, which is robust to motional heating and detuning. The preliminary experimental results are very promising too. On the top right, we see a picture from a joint work by Ziegen and Sophia on a dressed qubit driven by microwaves only. The dressed qubit has a much larger coherence time than the usual bare qubits, by about 3 orders of magnitude. Previous implementations used both microwave and RF fields, but we were able to develop an alternative approach which uses only microwave, which is a big simplification. The experimental results are very promising. Finally, on the bottom right, we see a new mixed dynamical decoupling scheme developed by the Jerusalem group. They combined the advantages of the well-known pulsed dynamical decoupling sequences with the also well-known continuous dynamical decoupling schemes. The new dynamical decoupling scheme is of potential interest to all experimental groups in this project. Finally, I am very happy to report that very recently, 2 groups in our consortium received very substantial funding from outside sources. Universal Quantum is a startup founded by scientists from University of Sussex, pictured here on the right, Winnie Hensinger, who is the head of the group, and Seb Waite, who is a senior researcher. They received £3.6 million in early funding from venture capital, with the prospect of further increased funding if the project succeeds. The news was all over the British media and not only, and here on the right we see a screenshot from the BBC website. Very recently the Hanover Group received considerable funding of similar size from the state of Lower Saxony. These 2 success stories give us a lot of confidence that the microwave approach is viable and very promising, even at the commercial level. Thank you very much for your attention.
Thank you very much, Nikolai. Thank you very much, Nikolai, for showing us the very promising approach of manipulating ions with microwaves. Okay, so thanks to all the presenters for these very attractive presentations about quantum computing. Now the floor is open for questions. Well, I have a few questions from David Shaw, so we will start with the first one, which is addressed to OpenSuperQ. And you would like to see how the project OpenSuperQ sees the likely future pros and cons of tunable versus fixed frequency versus parametric superconducting qubits.
Hello, and I also have my video on, and I hope the audio is okay.
Yes, we can hear you.
So first of all, on the theory and application side, the difference is a lot lower than you think. The expressibility of the gate families resulting from these 2 gates is extremely similar, and with good compilation, and software is always easier than hardware, that is not very different. We have very promising results with parametric gates and tunable couplers. However, and in the long time future, they may well take over. However, now that we are in the 3rd year, tunable qubits with fixed frequency couplers still constitute our critical path, whereas the other strategies are alternatives. And we know we can switch them quickly. The difference is much, much smaller than we initially thought.
Okay, thank you for this answer. We have another question, which is how do EU silicon spin qubit initiatives, iQubits, relate to the Quantum Flagship program? Well, maybe this is a very generic question, and there is no project which is represented here, which is developing silicon spin qubits. But there have been a complementary call in the Flagship program where a project developing silicon spin qubits has been selected. And it involves many partners, including CIViQ in Grenoble. So this silicon spin qubit platforms is also considered in the framework of the Flagship. Now we can go maybe for another question. There is, one very, I think, technical question. It's quite long, so I will read it. I noticed that composite pulses are usually used for high fidelity gates against pulse defects. Composite pulses are also used with single ion optical clocks against light shift in different targets. Is there a way to combine Han-Ramsey fault-tolerant pulse protocol with other hyper-Ramsey schemes to extract a better value of the BBR shift in clocks? Is there anybody who can answer to these questions about composite pulses?
I think I can answer.
Yes.
You hear me?
Yes, yes, sure.
There is way, and using composite pulses with atomic clocks already showed very good results and compensations of all sorts of errors. So I think there is quite a bright future in this respect, because it's just beginning the application of composite pulses there. So the answer is certainly yes.
Thanks a lot, Nikolai. Another question from Oksana Mishina. Question to Frank, once again. How powerful classical computer is needed to interface with quantum computer in your algorithms?
So for interfacing, once the infrastructure to run programs has been built, for interfacing remotely, you need to be able to run Jupyter notebooks, which almost all computers can do. The part that then will be run in a central facility is run in a high-performance computing center, but it's not their real big high-performance computers. This compilation is typically done by a decent beefed-up workstation. The calibration and optimization that we have shown as one of the key results to boot the quantum computer, that requires a serious cluster.
Thank you, Frank. Then I have a question, I think, for David. In which platform implementation will the rare earth ions in crystal be used? This is a question from Stefan Sescher from Infinium.
Yeah, so we do have different platforms in mind. I've shown two examples. One is a fully fiber-based photonic platform where the material itself is integrated into a fiber-based device, a fiber-based cavity. And in principle, it can be run all optically. We need cryogenic temperatures for that. So this is why we also consider and develop cryogenics for that. And another direction is to go into photonic integrated circuits. And one platform which we are considering in our consortium is to use lithium niobate, which is a tunable material, an electro-optical tunable material, where you can produce integrated photonic devices and realize multiple elements on a chip. But also silicon-based photonics is a possible route, or also silicon nitride. And this will require hybrid architectures where you combine different materials. And also in terms of the control, we have the optical control directly to control qubits and read them out, but also microwaves and radio frequencies will be applied. So there are various schemes. We consider 2 or 3 of them in our consortium, and then we need to see what has the best perspective.
Thank you, David. Now I have a question from Giulio from QSide. I think for Thomas, maybe. Does the thermal radiation from the silicon microchips affect the coherence of the ions? And how does this impact the fidelity of the single and 2 qubit gates? Thomas? Can you hear me?
Also, I can answer it because
you can.
We're using silicon microchips too. Thermal radiation is not actually the main problem, but rather the motional heating, which comes from random currents. Currently, the ions are situated about 30 to 100 micrometers above the surface, 30 micrometers for the oscillating gradient approach and 100 micrometers for the static gradient approach. And this limits the coherence time. However, with some mild cooling, we don't have to go to really superconducting cooling temperatures. Not only mild cooling helps a lot to fight this. But it is
from my side, with our ions, we don't see anything from black body radiation. So we know the shifts a little bit, but essentially we have coherence times on the order of a few hundred milliseconds. And it doesn't play any role whether the chip is warm or not. Like warm meaning whether it's at 10 Kelvin or at room temperature doesn't really matter. And it's the same also for the gate fidelities. To give you a feeling, the trap, the bulky ones that we have at probably around 100 degrees C, and we still get 99.6, 99.7, 2 qubit gate fidelities out of those systems.
Right. What is the distance above the surface of
so for the 3D traps, we have a distance of about almost 0.5 millimeter. In the surface traps, it's usually on the order of 100 to 200 micron.
Okay, thank you. Then I have a question from Oksana Mishina. What is meant by all Europe cryocooler, in particular all Europe parts?
Yeah, so to have a scalable technology, one needs closed cycle cryocoolers, which are free of liquid helium. And this requires a cooling machine that provides the cooling power initially. And so far, there is no really available European solution for these cryocooler heads. And so what we have been looking into in detail is how such a cryocooler head can be designed and optimized for the applications of rare earth ions, which need particularly low temperatures, down to 1.5 Kelvin, ideally even below. And this was done with a European company. So Thales was one of the contributors to that, with the goal to build a device which can be produced, which will be entirely based from European technology.
Okay. Thank you, David. Well, if I do not see any more questions on the Q&A, maybe I have a last question for Thomas. Is there any variation of the gate fidelity depending on the position in the ion traps, depending on the ion that is addressed?
No. Also there is a slight dependence if you go for longer and longer ions. And so there's a coupling to the motion. We managed to fix that now with multi-mode cooling, and at least up to 10 ions, it's essentially flat performance.
Okay, thanks a lot. So I do not see any other question for this quantum computing part. I propose that we move to the following part, which is about communication. And so the presentations of the following projects, so which are CiViQ, Kia, QRANGE, UNIQORN, and 2D SIPC. So the first presentation will be the presentation of CiViQ, and Valerio Pruneri is the coordinator of this project. And the subject of this project is about developing continuous variable quantum key distribution. So Valerio is professor at ICFO, and he has also made also work in the industry at Corning. So he has made many contributions to the field of photonics, to optical materials, multifunctional surfaces, and quantum optics. And today he will show us the results that have been achieved in the CiViQ project. So Valerio, it's up to you.
Good afternoon, my name is Valerio Pruneri, I'm from ICFO, and I'm going to present CiViQ, the continuous variable quantum communications project of the Flagship. So it's about quantum key distribution, where we use telecom technology with quantum security probes. The principle is based on modulated weak light and the use of quadratures, X and P, which are non-commuting variables. And in order to accomplish this with classical telecom infrastructure, we need to add quantum security proofs. We have to operate at the shot noise limited level. And especially important is the digital signal processing adapted to quantum security. Once we do that, we can avoid single photon technology. As I said, we can use a high level of integration through photonic integrated circuits. And in this way, we are compatible with modern optical telecommunication networks. The key thing of the project is to start from user and industry needs at network level and devise in a top-down approach the technologies we need, mainly at system level. Here are all the work packages. We range from requirements to network design, systems development, components for those systems, and also important is the post-processing and the security analysis. We have the full range of partners needed, which go from telecom operators, mainly with networks expertise, to integrators that provide subsystems and systems, to components and software developers, mainly small, medium enterprises and profit institutions, and last but not least, research centers and universities generating IP. And this is in a virtual cycle with positive feedback. The goals of the project are mainly three. We want to integrate QKD in a flexible manner and in a modular manner into networks. We want to develop high-performance subsystems and secure systems. And last but not least, we want to prepare for the next generation quantum communication systems. We will look now at the main results obtained so far during the project corresponding to these three objectives. So we have developed a top reference model for architectures. We essentially individuated in which types of architecture QKD systems make sense and defined the specifications. All these network requirements and system specifications also will be demonstrated in the field. We started doing that in the Open QKD testbed, and we have also devised the first version of a software-defined network QKD and a protocol stack for integration into classical network. We have to say that we believe that the quantum key distribution is an added security channel to the existing ones. In terms of subsystems and systems, we have developed an open platform, which is mainly based on off-the-shelf components. We have also increased the speed of continuous variable system, and we have especially investigated the coexistence with classical communications. Digital signal processing also for carrier recovery has been central to our work. We have designed and we are currently testing recently fabricated devices, QRANGE and transmitters, using photonic integration platforms. Also, a new security analysis for discrete modulation have been studied and proven. And last but not least, we recently experimentally analyzed the vulnerability of continuous variable QKD based on attack ratings. As far as the next generation quantum communication system is concerned, we thought it was important to devise a specification for the devices and the interchangeability of those into systems. We have groups investigating measurement device independent QKD based on continuous variable, even in unfavorable symmetric configuration. New CV protocols for quantum money and multi-user QKD have been defined. And last but not least, we have also investigated everlasting secure and high rate protocols in relaxed quantum computational security model. So all in all, we have filed 8 patents. We have also written up a 3 invention disclosure. Very importantly, we have generated 2 spin-off. One is already constituted, QUANT, and another one is incubating, very close to constitution, called Lux Quanta. Both spin-offs are supposed to supply in the future key system technology for quantum key distribution, mainly continuous variable. We have participated to a large number of conferences, especially invited talks. and we want to emphasize our presence in the standards activities. As far as the collaboration with other quantum flagship project is concerned, we have already integrated quantum random number generators from QRANGE into our QKD system, and here you have a picture of QSite QRANGE in a continuous variable QKD system developed at ICFO. Also, CNRS is doing the same. In KIA, very importantly, we are together making technological choices for critical building blocks for the quantum networks and integrating also network simulation tools into continuous variable QKD. In UNIQORN, we are developing joint test benches and especially defining common characterization procedures. And in a more specific topic, we are using squid light sources developed in UNIQORN for continuous variable QKD. An open QKD, even if it's not a quantum flagship project, is very important for testing the devices and the system developed in the quantum flagship. We are already started real-world demonstrations in Madrid, in Telefonica facilities, and CiViQ partners are also involved in an open call grant to demonstrate new protocols for multi-particle computation. Thank you very much.
Thank you very much, Valerio, for this presentation and to show us the significant progress that have been achieved on continuous quantum key distribution in the project CiViQ. Now the next presentation will be given by Stephanie Venner, who is the coordinator of the project KIA for Quantum Internet Alliance. Stephanie is also the vice chair of the Science and Engineering Board. So in the Quantum Internet Alliance, they want to develop the quantum internet, so achieve one of the ultimate goals of quantum communications. Stephanie is a professor at QTech at the Delft University of Technology. And she is very much involved in developing quantum communication either on the experimental or theoretical sides. She is involved she was involved at the Center for Quantum Technologies in the National University of Singapore previously from coming to Delft. And then she has developed this activity about the quantum communication. Well, she also contributed to launch the conference Qubit. And she is very active in this domain with many contributions both in the theoretical and the experimental fields. So now she will give the presentation about the results achieved in KIA. So Stephanie, the floor is yours.
Welcome to the Quantum Internet Alliance project. Before giving you an overview of our recent results, let me quickly remind you why we are actually pursuing the goal of quantum communication, to see how that is important for our project. Why does anybody want to do quantum communication? Probably the most famous application of quantum communication is secure communication, using quantum key distribution. However, many other possible applications are already known. One example is to perform secure quantum computing in the cloud. Here we use a very simple quantum terminal to access a remote quantum processor in order to, for example, perform a simulation of a proprietary material in such a way that the quantum computer cloud hosting company cannot find out what the material actually is that is being simulated on the machine. Many other applications are already known to exist, for example, clock synchronization, password identification, persistent verification, and many more. Quantum networks are not only useful to perform quantum network applications over long distances, but also at short distances to link together many small quantum computers into one larger quantum computing cluster. We are pursuing in our project. First of all, we would like to go beyond quantum key distribution. If we make all these huge amount of efforts in order to realize a large-scale quantum network, we would like to use it, of course, for secure communication, but we would also like to enable many other applications. And this has some consequences for our project. Specifically, one of our goals is to also connect quantum processors as end nodes to this network, on which more sophisticated applications can be run. We are also looking to develop applications software and a software and network stack that makes such a network universally programmable, such that potential users and customers can explore all kinds of possible applications on this network. In order to bridge long distances, we are working on quantum repeaters, and those could eventually be used to create entanglement over pan-European distances. We are also working on a network stack to enable fast and reactive control to mitigate limitations like memory lifetimes in quantum hardware. Finally, an important part of our project is also to determine what to do next. To this end, we are developing a blueprint for a pan-European quantum network architecture. Let me remind you of the partners and their roles in our project. We have 23 partners in total, including many academic institutions, industry engineering components for a quantum internet, industry that is looking at actual real-world use cases of such a network, RTO, supercomputing facilities that we use for our blueprint simulations, and we engage with the existing classical internet community, for example, via RIPE NCC. We are talking to many other players, for example, network operators, QKD industry, or also potential end users. Let me now remind you of some of the goals and give you some of the highlights of what has already been achieved in our project. I would like to emphasize that many things have already been achieved, including also patents that we've written on this, but I cannot cover all of this in this short talk. First of all, our goal is to create the first multi-node networks linking few qubit quantum processors. And we do this in order to perform tests of quantum protocols on such multi-node networks that allow us to push beyond the state-of-the-art two-node links, benchmarking entanglement and teleportation across a range of possible experimental platforms. Multi-node network experiments are underway with nitrogen vacancy centers in Delft, neutron atoms in Garching, and ions in Innsbruck. And I'm happy to report that we've now also entangled 3 quantum processing nodes based on NV centers in Thailand. Industry is finding solutions that are broadly relevant for European quantum technologies. To give you just one example, Toptica has developed a narrow linewidth laser system for frequency stabilization between remote network nodes. In order to bridge long distances, we are working on key capabilities for. And to mention some highlights, we've achieved a world record in the storage efficiency of a quantum memory that is important for realizing quantum repeaters. We've achieved telecom-heralded matter-matter entanglement. We've also increased the amount of multiplexing in such a quantum memory. And we are working on enabling technologies such as, for example, field-compatible cryostats for solid-state quantum memories, fiber-link phase stabilization, and fast photon counting electronics. In order to make this all useful, we're working on the first demonstration of a software and network stack, also to working towards our planned system test, where we plan to showcase blind quantum computation on a remote quantum processor using both NV centers in diamond and ions. In the domain of integration and control, we have constructed the world's first quantum link layer protocol and designed a quantum network stack. We are now implementing this on hardware in our control system called Q1S that provides a hardware-agnostic interface for quantum network applications. Local node instructions have been tested in the lab, both on NV centers in diamond as well as trapped ions. So the concept here is that the user can, in platform-independent software, in the future, write all kinds of applications to run on a network without the need to understand whether the underlying platform is actually NV centers in diamond or trapped ions. We are also looking to develop real-world use cases and find actual hardware requirements for running application protocols on such a network to guide future design. With this in mind, please have a look at our quantum protocol zone that collects protocols for a quantum internet with a focus on making them easily understandable and implementable. This has already been used during hackathons with industry for market research and research surveys. We're also looking at the benchmarking of protocols and functionalities in the light of industry needs and wants for a quantum network. And in progress is a library of use cases and figure of merits to consolidate industry interest for developing proof of concept. Finally, I briefly want to mention our efforts to construct a blueprint for a pan-European quantum network architecture to answer the question of how we can scale beyond our project. Finding such a blueprint starts with, as input, a real-world network fiber topology. For example, the one here from the Netherlands, from SURF. We've developed an algorithm to perform a pre-optimization of repeater placement to decide where on this existing quantum network infrastructure are we going to place quantum repeater nodes. We've developed simulation tools and hardware models for Kia platforms so that we can actually explore and test possible network architecture designs. We've developed a machinery for parameter optimization using machine learning that can be used to find minimal requirements of quantum network hardware. In the second part of the project, we will then determine the requirements for a pan-European network. If you want to know more about our project or to get involved and read news, please come to our website, quantuminternet.team. Thank you very much.
Okay. Thank you, Stephanie. And then we have the presentation of QRANGE by Hugo Sbinden.
Thank you very much for this introduction. Can you see me and my slide?
Yes.
Okay, excellent. Okay, so I'm Hugo Sbinden from the University of Geneva, and I would like to present you our project QRANGE, which has a goal to produce quantum random number generators, which are faster, cheaper, and also more secure. As you can see, we have a small consortium with a few 5 universities, 3 companies, and some research institutions. So this is kind of the overview of the project with the different work packages. So we work on system architecture and use cases, certification, of course also concepts and theory, and most importantly, we will develop 3 kinds of prototypes. One which should be very cheap and compact, one which should be more secure than what is existing up to now, and finally one which should be much faster with the order of more than 10 gigabits per second. So in the first part, we produced a document which analyzes different use cases and requirements for our random number generators, and also defines the system architecture we need to develop to address these use cases. Then a very important part is the certification. If you want to sell a product in this security business, you This is an important point. So in this work on certification, we have 3 objectives. The first one is actually that we study different attacks, which is symbolized here. Now you can give to some attacker more or less access to device, and under different conditions you have different results. Another important thing is that we have to make sure that our devices will be according to some existing standards that exist already. And finally, we also would have some certification which takes in account the specific properties of a quantum random number generator, which has, of course, some advantage with respect to true random number generator. And an important step in this direction is this document where we contributed a lot from the ITU, which makes some recommendations for quantum random number generators. Okay, let me come to a first prototype we're developing. So here you see a silicon chip, which is a test chip. And on this chip, you can see here that we have different test devices. And a test device consists of a emitter, which here in the center, and single photon detectors which all around this emitter. You may know that in silicon it's not so easy to make a light emitter, so we do that by using a PN junction, which we reverse bias, and you see this little light which is emitted by this emitter here. Now the randomness is generated by measuring the arrival time of the photons, or the detections. So we send quite long light pulses, and you see here now in this graph here, you see the probability to detect a photon at a certain time. So we encode the time of detection in an 8-bit number, and you see this homogeneous distribution, which is a good indication that this result is actually indeed random. Now let me come to the second approach, which is the self-testing QRANGE. This is very much inspired by the device-independent approach, where you look at actually a device-independent Bell experiment. So we have Alice and Bob, and you give some input and you get some output. So in this semi-device independent scenario, we have on Bob's side, we have a black box. We don't have to make any assumption on Block's side. However, on Alice's side, we have a few assumptions. So our assumption are very simple. So one assumption is that we don't have a direct channel from Alice to Bob, so they don't communicate. And then the states we send from Alice to Bob have a limited energy. By doing this, now what we can do, we can actually estimate the entropy we generate by making an analysis of this conditional probability. So if we get have a certain input here, a certain state we send, we analyze just the outputs we get. And based on that, we can calculate the entropy. So this is a realization we made this year. Now you see what we use. We use 2 coherent states where we can modulate the phase, and we make measurement with a homodyne measurement, with a local oscillator and so on. So if these states are weak, so we have this bound on the energy, there is an overlap here. And so in this, since these 2 states overlap, and even in practice, in theory, you cannot distinguish them perfectly. So here we generate the randomness in our output. And you can see we can obtain up to 140 megabits per second. The nice thing about this approach here is that actually can be implemented in integrated chips. So this is a picture of the first chip we produced in collaboration with Fraunhofer, and we have to test this now. I could also mention that this concept of self-testing, we also implemented together with our colleagues in Trento on a silicon chip. Now let me come to the last approach, the fast one. So here the entropy source is this phase diffusion process in a laser. So we have a pulse laser, and each pulse has a random phase. So now if we send this pulse into this unbalanced interferometer, we can have interference here at this point between succeeding pulses. Now, since this phase is random, of course, this interference will be random, or the outcome will be random. On this detector, we have a random amplitude. So this is the scheme, and practice is a little bit more complicated, no? But still, so we have this random laser pulses, random phase. We convert this random phase with our interferometers in some random amplitude, and then we convert this signal into an electrical signal, we digitize it, and then we get this distribution here, and we can extract random numbers, which we then send to our application. So here below you see a little picture of this device. So you see that fits in a 90-inch rack. You see a top view, and what you can see here that is it generates random bits at the rate of 2.75 gigabits per second. So we are not yet at the 10 gigabits, but this is just the first device. The applications are for this random number generator, in particular QKD, and Valerio just before mentioned that we have a collaboration with CiViQ where these random numbers are used for various QKD systems. Then, of course, we have a theory and modeling activity. It's very important that we make a precise model of our random number generators in order to have a good certification of the entropy we generate. So here you see, for instance, a scheme of a fasted random number generator I just presented before. And we are now writing a review on all these aspects of physical modeling of quantum random number generator. Here on the other side, you see a calculation we can make in order to estimate the entropy in the self-testing device. So we see here these two E1 and E2, these are the correlation factors which calculate the correlation between input and output. And you see if we have in this region here where we have strong correlations or anti-correlation, we have a high number of entropy we generate. This entropy here in bits per round. This you can find, this analysis can find in this paper here. And then also we work on future approaches which are more fully device independent, taking account fully device independent scenarios. Okay, I'm coming to the end of my presentation. You see here a little overview of our activities in dissemination, exploitation, and communication. And if you need or you're interested in more information, please visit our website. Thank you very much for your attention.
Thank you very much, Hugo, for this very nice presentation about the various kinds of quantum random number generators. Now we will move to the next presentation, which will be given by Hannes Hubel from AIT, Austrian Institute of Technology, and he is the coordinator of the project UNIQORN, which aims at developing various kinds of components for quantum key distribution devices. So, Hannes, the floor is yours.
Thank you very much, Thierry. Yes, my name is Hannes Hubel. I'm working at the Austrian Institute of Technology. And today I would like to tell you more about the UNIQORN project, its goals, and more importantly, the results we achieved over the last 2 years. So we heard in the last presentation how wonderful quantum communication is, offering blind quantum computing, offering secure communication, but why don't we have it already? Why is there no quantum communication devices in data centers, in our offices, or even in our homes? And there are several roadblocks which basically prohibit a full rollout of this technology. And the first one is that although quantum communications is a disruptive technology, nevertheless, it will not in the short or medium term fully replace classical optical communication. So that means we have to work together with the classical optics side. We have to make sure that our new systems and devices can be integrated into existing optical communication networks. And the second part is that we need those systems to be smaller, more cost effective. We just seen it in the previous project where they also want to basically make a very small, cost effective, robust QRANGE. And this has to be expanded not only to QRANGEs, but to other quantum communication systems like QKD systems or entanglement sources. And this is the goal of the UNIQORN project. So here is basically listed our objectives. So what we want to do, we basically want to generate a full value chain for quantum communication, starting off with the photonic integration with systems on chip. So we basically want to bring those large setups, which are currently operated in labs all around the world, doing quantum communication experiments, and put everything on a very small chip so it can basically fit into your modem or maybe later on even to a handheld device. But this is not the end to have just a chip. What's also important is basically the system integration, assembly of the chips to larger systems, packaging, so putting electric leads on it, putting optical fibers on it so you can really go out and make field tests. And there also, the UNIQORN project will contribute. So we have basically several field deployments planned at the end of the project. We basically will test our systems in real world applications, which were also developed, some of them during the lifetime of the UNIQORN project. Of course, this is only possible if you have a very, very strong consortium, and I'm very happy to be in lead of such a fantastic group of people. So again, we start off, we have a very diverse consortium. We have basically the academic groups on board, RTOs on board, but also small and medium enterprises and industry. And they all come with different backgrounds, which you basically need to have this full value chain. So we have basically the quantum scientists, which have basically come up with the theory, description of the quantum mechanical processes going on in order to make the systems. We have the RTO, which basically designs systems around those processes. We have fabrication partners, which basically produce the chips. We have packaging partners, which basically will put the optical fibers, electronic leads on it. Also design and automation, which is needed in order to plan ahead, simulate the systems even before you start assembling it. And finally, we basically have the integration into existing telecom infrastructure, which we basically do together with network, telecom operators and also a network group. Good. Let's come to some of the results of the UNIQORN project. So the most part of the first 2 years was basically spent designing and fabricating those system and chip. And I'm really happy now to show you a couple of them. The first one is based on an indium phosphide platform. So what we have here is a small chip 4 by 2 millimeters, which basically contains a full QKD transmitter. So we have here, so on top here is the layout of the chip. So we have basically here a laser section. We have then a phase modulator, some Mach-Zehnder interferometers in order to do some pulse carving, and a variable attenuator, which basically brings the signal down to single photon level so you can actually run a QKD protocol with it. And as I said, this whole chip basically represents the transmitter, and the aim is to basically demonstrate a very low cost QKD transmitter running, of course, on a lower rate than some of the other QKD implementations already. And what you can do then is to share the cost of the receiver, which is more bulky because you need single photon detection, among many of those low cost transmitters in order to bring the cost down for the whole network. We also have some additional silicon-based components developed in the project. So we have now a 1x16 SPAD array. So SPAD stands for single avalanche photodiode. So you can really detect single photons with this SPAD array. What's really nice, that is basically room temperature operation possible. So you don't need to cool it anymore. Again, with the idea of putting it into really systems which you can put on your desk, which don't require excessive cooling. And we have very high quantum efficiencies here and dark count rates below 100 Hertz. What's also nice on those chip is that it's not only the optical part which basically detects the photon, but we also have a processing logic here which already performs a kind of pre-sifting of the results. So that means, and digitizing it. So that means you don't need any additional electronic components anymore to interface it, the photo detector, with your computer. You can read it directly in and do some digital post-processing. We also have then for CiViQ QD, so that was mentioned by Valerio in the CiViQ project, which basically deals with a continuous variable detection, QKD, where you don't need a SPAD array anymore, but you basically need a balanced receiver. And the UNIQORN project has built a very low noise transimpedance amplifier for those balanced receivers, which have a 1 GHz bandwidth. So that's for very fast QKD systems. And we're working together with CiViQ to test out and characterize those amplifiers. On the next slide, we have some more modules, this time not on indium phosphide, but on a polyboard platform with a hybrid integration approach. The advantage here is that you're not limited anymore by the physical properties of the material, but you can really have a polyboard platform with waveguides and then basically put micro optical elements on top of that. And so basically massively increase the different possibilities of components you want to put on there. And we, for example, developed now a polarization entangled photon source. So here you have the layout where you have a pump light coming in, green. In this case, we have our nonlinear crystal here, which generates the entanglement. The entangled photons are actually at 2 different wavelengths, so they actually split here via a dichroic mirror. One photon comes out here, and the other one comes out here. And on the right-hand side, you basically see the fully assembled source with fibers pigtailed. And again, the whole source is basically just a few millimeters or a few centimeters in size. On the bottom here, we basically see the wafer chip for the source here. And as you can see, we can really go with the wafer approach to high volume fabrication of those entangled photon sources. We don't only do polarization entangled photon sources on the polyboard platform. We also have a quantum random number generator, which is basically depicted here. We have a heralded photon source, which is here, where you basically herald the generation of one photon by detecting the second one. We have a squeezed light source. And what we also want to do with the SPAD array, which we have developed, which I spoke before, we want to basically integrate that together with the polyboard. So we have on-chip detection of photons as well. Okay. Apart from the hardware developments, I would like to show you here a simulation suite which was developed by our partner VPI. This is basically an add-on package to a commercial product they already have for quantum communication systems. So you can basically design systems based either on continuous variable or discrete variable QKD systems. You can also study links in coexistence schemes. We have the quantum channel and the classical channel, and basically simulate the performance of this. It's very easy to use. So you don't need to be a quantum physicist. So it's really designed, it's really made for optic engineers. You can basically drag and drop your different components, detectors, lasers, modulators, and build up a full system. And we basically use this one already now to simulate first our DPS transmitter, so the one I showed a few slides previously, and the results are really good in comparison with the real device. So you can really use this simulation tool to design your QKD system even before you buy or fabricate your first component. And the beta release is now available. So if you're interested in trying this out, either contact VPI Photonics or contact me, and I can make the contact with them so you can try out the software. Okay, let's come to the few last slide where we were working on the higher levels, on the application sides, deployment sides. We have one deployment site in Bristol where they have a fiber network in the city. Here we want to test QKD links for 5G application, so securing edge computation. And in order to have basically a network where you have several links, we have optical switches which basically control the different links of the QKD system using an SDN controller in order to maximally use the resources of the network, so you generate maximal key rates between all the nodes. We also have some additional links and have some aggregation nodes again where key management plays a role. We basically build up a lot of key material between those two nodes, which has to be then dynamically shared among the other nodes depending on the load of the network. Another application, which is, I think, maybe more interesting to the people, to the listening in now, is fiber to the home QKD network. So that's together with Cosmote in Athens, where we really want to use a deployed fiber to the home network, where basically you have one large distribution site here, and you have basically many end users on the other side to use our QKD approach, where we have those very cheap, low-cost QKD transmitters on the right-hand side and the more expensive bulky receiver on the left-hand side, to demonstrate that you can basically run QKD even in this scenario, which is quite demanding because you have a lot of splitting here, so you have quite a lot of loss in a passive optical network, and show that QKD is really something for the home user as well. On the next slide here, we also, apart from QKD demonstrations, we also want to go beyond QKD. So we have quantum network, a dynamic quantum network router where we use entangled photons in the network, and we have basically a wavelength sensitive switch here, which splits the wavelengths coming out from our entangled photon sources and distributes it to different users. And by using an optical switch in addition to that, we can basically dynamically route the entanglement to different users, and then basically entangle two different users at a time together, and we can change the combination in the network. And finally, we also want to demonstrate one-time programs. So that's basically quantum algorithms where the user can only execute the program once and not more often. This we just investigate currently for digital payments, if there's an advantage using this protocol. And we also implemented QRANGE integration into a commercial network card provided by Mellanox, where basically the two cards now open up an IP secured tunnel based on the input from the random numbers. And that really shows that now commercial network devices are quantum ready. So that's, I think, quite important to really make sure that network devices can accept keys or input from quantum devices for their internal protocols. In that way, we can basically really roll out the quantum technology very fast without having to basically change every device in our networks. Okay, that brings me already to the last slide. Thank you very much for your attention. If you want to know more about the deployments or about our evaluation of our systems, you can look on the webpage or follow our Twitter feed.
Thank you very much, Hannes, for presenting us the impressive developments of the technology for quantum key distribution. Now we are coming to the last presentation of this session, which will be given by Dmitry Efetov, who is at ICFO in Barcelona. And Dmitry is the coordinator of the project 2D SIPC, which develops two-dimensional quantum materials and devices for scalable integrated photonic circuits. So
thank you very much. You can hear me, right? Okay.
Yes, yes.
Okay, so basically, right, so 2D SIPS deals with quantum materials and devices for scalable integrated photonic circuits. And we are a consortium which consists of several key players in the field of 2D materials, including myself, Frank Kopens at ICFO, Andrea Ferrari, Medad Jura and the University of Cambridge, Vladimir Falco and Konstantin Vasilov in Manchester. Then a photonics group in Marco Romagnolo and CNIT, and a single photon detector company in single quantum from Delft. And so the main sort of issue which we're trying to solve is that quantum networks are building blocks for quantum information, quantum computing, as well as quantum communication. And quantum networks are usually extremely bulky. So a picture from Delft here shows that sometimes connecting to quantum nodes requires entire laboratories. And proposition already dating many years ago is that one can use integrated photonic circuits to miniaturize these optical laboratories and deposition all the active elements on a silicon photonics chip. Here, the key ingredient is that one needs to introduce novel materials into the photonics network, which then are the active elements of the processing here. So we need detectors, we need light sources, we need modulators, and this can be integrated all in one chip. The problem why this is very hard is that it's from material point of view, it's really hard to grow all of these different materials in a compatible way on top of such circuits. And this is the main sort of target of our consortium, is to actually build up entitled photonic circuits with single photon emitters, single photon processing units, single photon detection, entirely from two-dimensional materials. And the advantage of two-dimensional materials is that they're actually easy and non-invasively integratable into silicon photonics. They're mutually compatible and scalable. Also, I will show that these type of devices offer entirely new possibilities in terms of quantum emission, modulation, and quantum detection. And last but not least, the goal of this consortium is really to demonstrate integration of all these devices on a silicon photonics platform and the mutual operation of all these devices. So the reason why 2D materials are special is because they can be prepared in room temperature, and there are very different varieties of two-dimensional materials, which can be also stacked non-invasively into van der Waals heterostructures. So it is possible to use different material species, but then also to combine these to prepare novel material properties. And really, in the last couple of years, many such materials were discovered in their two-dimensional form. So it ranges from Dirac materials, Weyl materials, and topological insulators to superconductors, ferromagnet nets, and of course, semiconductors. And basically, the other advantage, as I said, so because these can be prepared non-invasively, also a variety of works have shown that these can be easily integrated into photonic circuits. And so, for example, we in the past presented ultra-fast modulators and phase modulators, as well as single photon emitters and detectors, which can be integrated all together on a silicon photonics platform. So our consortium, again, consists of University of Manchester, who are the world leading group in the preparation of two-dimensional materials and heterostructures. So their goal is to find novel 2D materials and identify promising materials for applications. Then UCAM deals mainly with single photon emitters from these two-dimensional materials. ICFO is primarily working on single photon detectors from newly discovered 2D materials. CNIT is providing the silicon photonic circuits, and Single Quantum is in the end responsible for the integration of these devices into industrial cryostats and disseminating these results towards the other more mature pillars. So some of the key results which we have achieved is, again, so Manchester, ICFO, and UCAM have been identifying novel optoelectronic materials, including indirect exciton systems, which are realized in heterostructures of different semiconducting materials. And they were able to show that really one can tune the emission wavelengths accordingly, depending on the exact stacking and combination of these materials. So they have shown also that these emitters can be controlled by gates, so just by applying voltages. Then UCAM has then used these materials to integrate them onto nanopillars. And the strain induced in these nanopillars creates a single photon emitters, which can again then be tailor-made in their wavelength. So this is all tunable here. The advantage, of course, is also that the emitter arrays allow for ultra-bright sources and deterministic placement of these single photon emitters. And here, some of the examples are that UCAM has observed the longest indirect exciton lifetimes of 0.2 milliseconds, which have been reported in any such materials, which is then interesting for quantum simulation and communication. UCAM has also demonstrated a new approach to create these single photon emitters by, again, integrating these array platforms. And this can be particularly interesting from quantum communication information processing. And ICFO has further demonstrated world record tunability of single photon emitters for quantum communications, where they were able to show that certain gates can tune this with gigahertz frequencies. So turn on and off single photon emitters with this type of frequencies. Then the other direction was towards single photon detection. So here ICFO pioneered the discovery of novel superconducting materials in the namely magic angle bilayer graphene superconductors. So these studies were published in many Nature papers and was covered by the New York Times and Le Monde. And these materials, what's so special about them, they have by far the lowest carrier density and strongest coupling of any superconductor. And they're, as I will show, they're ideal for a long wavelength single photon detection. So in particular, we have shown that these are ideal terahertz single photon detection materials, technology which currently just doesn't exist. And in this regard, a paper came out 2 weeks ago where we were able to integrate superconducting graphene into superconducting circuits and use them as detectors for gigahertz frequency. So here we have shown that such detectors have the sensitivity of a single 32 gigahertz photon. So this is really a new capability to sense single photons in the gigahertz. These detectors have 99% quantum efficiency because they're integrated into resonators. And actually a follow-up paper, which will come up in the next couple of days, is that we really showed that this type of detector can be used as a single threshold detector for really quantum communication protocols. So with this, we have also extended single photon detectors towards higher temperatures by using high temperature superconductor. And we have shown that some of these 2D materials can actually be pushed above liquid nitrogen temperatures, which potentially would be a route to reduce the cost of single photon detection applications. Last but not least, all of these devices are currently being integrated into silicon photonics circuits here. CNIT has already designed the chips, which can be seen here. So these electrodes, for example, they are hosting already graphene modulators, and other sites here will be hosting the detectors and emitters, which can be then read out at the same time. And all of these chips are made compatible so that it can be directly packaged into the commercial cryostats by single quantum. So these are, so with this, I think I want to just go quickly through the accomplishments. So we have published more than 19 papers, some of which are extremely highly cited and free in Nature. We have been covered in the New York Times, Le Monde, and Physics Today. We have participated in more than 50 conferences as invited speakers. We have now filed 13 patents, and 13 patents and 30 patent applications were submitted. And because of the New York Times article, we were also covered internationally in media, and we achieved more than 19 million hits because of our dissemination activities. With this, I want to wrap up. Thank you. Thank you very much.
Thank you very much, Dmitry, for the presentation of the impressive results achieved in the project 2DSP. So I would like to thank also all the speakers of this session, because we are at the end of this communication pillar. Now the floor is open to questions. So I have a first question from David Shaw. which is what are the strengths and weaknesses of EU quantum communications program versus the current state of progress in China? I think this is a question for all of you. Yes, one point that I also wanted to give is that unfortunately Valerio Pruneri and Stephanie Venner cannot be with us today. So the question will go to the 3 other projects. So maybe I read again the question. What are the strengths? Okay.
I can start maybe.
Yeah.
Let's start with the weakness. Maybe I think it's definitely in a country like China. I think it's much easier to basically focus a lot of effort, a lot of money, resources on single topics, like they shown, for example, with the QKD satellite they launched. I think those programs are much harder in Europe to get started because, yeah, you have a lot of input, a lot of different interests from the member states. So I think it makes it easier in one country to basically bring all the resources behind you. But then I think on the strength, I think Europe is still basically leading in quantum technology, in basic research, quantum communication for sure, and I think even quantum computing, quantum sensing, I think Europe is doing really, really great. So I think what we need is basically to harness it, find maybe additional money, find industry who is basically really interesting to basically make out technology of this.
Okay, thank you, Hannes. Anybody else to comment on this, the situation between Europe and China?
Maybe in China they have less paperwork to do and less administration.
Yes, certainly. Well, maybe they have other constraints, you know. Nobody knows, but well. Okay, thank you, Igor. Now we have another question from Oksana Mishina. Among industry partners of your projects, what was the level of quantum readiness education in quantum-related topics of the working personnel you interacted with? More general question about education.
Maybe I make a start again.
Yes.
We basically at the beginning of the project, so at the kickoff meeting, I made a crash course basically for quantum communication to all the other partners. Yeah, I think I think the level was not very high, but I think it's also true that for the quantum physicists, the understanding of applications and network technology was not high either. I think it's just naturally those are 2 different groups which are really starting to meet up now, which is very important. And I think we just have to basically try to cross-pollinate as much as possible those two groups and work closer together and have maybe in the training, in the education at universities, special programs which basically teach new students something about from both worlds.
Yeah, I think this is absolutely true, and there is cross-fertilization from one side and from the other ones also. Because when you speak about security, then people really dealing with security have many things to teach to physicists.
Yeah,
I think.
Absolutely correct.
Okay, so are there other questions from the audience? Well, I don't see any. Maybe I have a question to Dmitry. Dmitry, you showed us very efficient and very performant bolometers, and I wanted to know how they compare with the usual, I would say, SSPD, superconducting single photon detectors.
Right. So they cannot be directly compared because usual single photon detector operate in neo-IR. So those are highly energetic photons. And the photons which we are able to send, they're more than 100 times less in energy. Okay. So in terms of capability, normal single photon detectors stop working in the neo-IR, so it's around like 8 micrometers. And really our detectors work in the terahertz and in the gigahertz, and there's really no comparable technology.
Thank you for this clarification. maybe another question to all of you. What appears in your presentations is that the integration is really a key element for improvement of the quantum key distribution or quantum communication devices. And could you give us an idea of the improvement of the performances which are brought by the integration? Or is it too early to ask this kind of question?
So for our project, we are basically now the first, I mean, the devices that have been fabricated are packaged. So we're just waiting now for the first evaluation results. But I would say even if they are maybe not more performant or maybe slightly less, I think you still already gain a lot by simply the manufacturing process, reliability, and cost effectiveness as well. So I think one should not necessarily just compare the performance of the device then, but the whole fabrication process as well.
Maybe just to add, so I think besides, so I think the first goal is just to have similar performance of these detectors, but now integrated on chip. And that would already allow the same performance, but in a miniaturized version, which is much more applicable.
Yeah. Thanks a lot. Well, I still have one or two additional questions. I do not see any other question from the audience. But Hugo, you mentioned the certification of the quantum random number generators. Are there similar, for quantum random generators, are there similar tools than the one that are existing for classical random number generator, or is it yet to come?
Well, I think at the time being, the certified quantum random generators, they really just are judged with the same rules, with the same certificate process like true random number generators. What would be a goal, of course, or nice to have, is that you have a specific class for quantum random number generators. But that's, of course, something which doesn't depend on us. It depends on this certification organizations, and there is a lot of work to do in order to convince them that there could be some advantage of quantum technology with respect to normal classical technology.
Okay, thank you, Hugo. I do not see any other question coming from the audience. Well, anyway, we are already at the end of the session, so I propose that we close this question and answers about communication now. So I would like to thank all the speakers of this session of communication. We are, in fact, at the end of these two sessions that were on Tuesday and today about the reports of the Quantum Flagship projects. Clearly, there were a lot of very first-class and very important results that have been achieved by all the projects in the various fields that have been that are addressed by the Quantum Flagship. The results are very impressive. So I would like to thank all the speakers from yesterday for their very impressive presentations. And so I would like then to close the session and thank all of you very much for your efforts and for the quality of the result that you have shown. So. Okay, thanks a lot. Bye-bye. Bye-bye.
Bye-bye.